After a very good presentation on intents by Li-Fi and Philip, now we have Aryeh Greenberg, who will be talking about confidential solidity and ERC-7984. On this topic, I'm really excited because as we move a little bit closer towards confidential compute and privacy, this is going to be really, really interesting. Aryeh, are you ready? Over to you. All the best.
Thank you so much for the intro. I'm Aryeh Greenberg. I'm a developer at OpenZeppelin, and I'll be speaking about confidential solidity with coprocessors and ERC-7984. Before I start, I want to get a show of hands of how many people here have written smart contracts before in general. OK, almost everyone. And how many people have written smart contracts using confidentiality or privacy in some way? OK, very few. Good context. OK, so we'll start off with what we're going to be going over here. We're going to start off with coprocessors, just in general, so that you can understand the tech and how this is working, which is really crucial when you're building confidential contracts using coprocessors. Then we'll get into how the Solidity interacts with it, the token standard that we at OpenZeppelin have built, along with Zama and Inco, ERC-7984, and then we'll do a quick demo using the OpenZeppelin library and deploy a token and interact with it. So to start off, what is a coprocessor? In traditional computing, a coprocessor assists the CPU, right? The CPU gets a task, and the CPU is like, do I have someone else here who can help me out do it a little quicker? So you'll have dedicated units which are helping the CPU accelerate the tasks. The CPU will delegate a task that comes in to, for example, the FPU, floating point unit, or some others, some examples above. When we get to the EVM, it's basically the same thing, right? The same concept carrying over. The EVM will delegate via smart contracts to a coprocessor, which is dedicated to doing a specific use case and will either accelerate it or make something that's not possible. So coprocessors generally will monitor for events or other on-chain activities and trigger computation based on that. So your contract can emit a specific event, and if you have a coprocessor wired up to it, it will be looking for that and do something based on it. And then the EVM can accept information back from a coprocessor via some sort of attestation, generally signatures from maybe an MPC network or ZK proofs, something like that. So how do these coprocessors enable confidentiality? There's two main ways that we have been working with, two main systems for these coprocessors, which are FHE, fully homomorphic encryption. So with FHE, you have ciphertexts that are quite large. Those are stored on the coprocessor. And you'll have handles that there's a mapping of handle to ciphertext. And on the coprocessor, it will do the FHE operation. None of that actually happens on Ethereum. And that makes it relatively cheap to do on Ethereum, where all the excess computation is delegated to the coprocessor. Another method is TEEs, where the coprocessor is a trusted execution environment with a private key stored inside the coprocessor. Inco is working on a solution using TEEs and decrypts, operates, and then re-encrypts on the coprocessor. So all that is opaque to the EVM and the outside world. So before we get any further, we just want to define what confidentiality is here. Sometimes it's a little confusing. In a general public transfer, right, on Ethereum in the EVM land, you always know who's involved and the amounts, right? So the from, the to, and the amount is public. When we're talking about confidentiality, what we mean is that amounts are always obfuscated. So you're not able to figure out the amount unless you're involved in the transaction, but other people know who is involved parties in the transaction. And this is because we don't have stealth addresses. We're still using the Ethereum account-based storage management. So you'll have mappings of your addresses, and when that changes, everyone knows that changes. But what it's changing to, people can't see. OK, so we've defined a little bit about coprocessor. Now let's get into the specifics of how you'll interact with them using Solidity. So for any code examples here, we're using the Zama FHE, FHEVM examples just for simplicity. The primitives will carry over to other coprocessors, pointer-based Solidity paradigms. So over here on top, we have the integer representation of 64. right? Unsigned integer. Oh no, 100. My bad. And on the bottom we have encrypted integer, unsigned integer for 100. So what's the bottom value? We'll get to that later. What's the top value, right? Pretty simple hexadecimal. So value representation is a bit different. Now, if we want to do an operation, right, within Solidity, simple, we have bitwise addition. So 100 plus 100 equals 200. But with encrypted integers, right, what's the answer to this? I don't really know. Technically, yeah, I can do bitwise addition, but certainly that is not the solution, right? 100 plus 100 with handles is not the bitwise addition. So let's get into what these handles actually are. So the handles are a handle to external data, a pointer to somewhere else. So you can kind of think of it as a storage slot. You have that in storage, but you don't know what the value is unless you fetch it. And the way you fetch it is a little bit different. So the first 21 bytes is entropy, which is just a hash. The next one is 1 byte of the index, which isn't so important right now. We have 8 bytes for the chain ID, 1 byte for the type, and 1 byte for the version. So this is what our contracts can see on chain. So, like, what do you think you can do with that? You can't really do much with that on your own without help from the coprocessor, right? We don't know the value. If you see a long string of bits that represents 100, you have no way of getting that. You're not able to branch. You're not able to revert based on it. And you can't use native operations. You can't do, right, just you will add with those. It doesn't mean anything. So the way that it works is generally you'd be calling a single contract which represents the coprocessor on the chain. So for example, on Ethereum, you would have an executor contract. And on that contract, you'll have a bunch of exposed functions, for example, add, subtract, multiply, divide, and you would pass handle A, handle B, and it will deterministically produce handle C. And it will emit an event of this operation, and the coprocessor will be watching it. And the coprocessor will observe that I want to add handle A and B, and the result is C. So the coprocessor will look in the mapping, it will see handle A results in ciphertext A, handle B results in ciphertext B, and let me add them, and then I get ciphertext C, and I store it in the coprocessor at handle C. So that's how the coprocessor will react. That's how Solidity will interact with the coprocessor. And then if you actually want to figure out what the value is, you have to send a request to the coprocessor for decryption, and then the coprocessor will send back the result along with an attestation, generally a signature. So who can actually use these handles, right? So we have confidentiality, and I said, right, you can decrypt it, you can operate on it, but who's able to do that? Since it's confidential, obviously not everyone can. So we have the concept of an ACL, an access control list, and to utilize the handle in any way whatsoever, you must be permitted explicitly on the ACL. So any account with permission on the ACL can do any operation, can decrypt, and it also can pass on allowance to another user. Just for some context, if you bring a new value into the confidential realm, you generate a ZK proof that you know what that value is, and then you get added to the ACL for that value. So no one can get access to a value without knowing what it is, but once you know what it is, then you have access and you can give others access. Okay, so we've built on these, we've kind of defined the primitives in high level. Now, how do we build a token using these primitives? So at OpenZeppelin, along with others, we built ERC-7984, which is a token that's optimized for using handles, for transfers, events. All of it is using handles. So, right, that means that it's agnostic to what the actual implementation is. You can use any coprocessor implementation with it, meaning it can be utilized for FHE confidentiality, TE confidentiality, or other schemes, or even token systems that aren't confidential, but gain from pointer-based storage. So again, it's fungible like ERC-20, and it enables confidential on-chain transactions. The addresses are always public, while the balance is involved in events, and balance on-chain is private. So how do we do this? Right, getting back to the concept of handles defining value representation, defining operations, right? ERC-20, ERC-721, you always agree on how your values are represented, right? Unsigned integers. You always agree on how you're operating on them, addition, subtraction, simple bitwise. With ERC-7984, we diverge from that, right? So we redefine value representation. Again, handles can be anything you want, and we redefine operations. And this brings up some interesting topics where, right, if you have multiple tokens, you have different confidential contracts that don't agree on value representation, that don't agree on operations, how do they interact? And the answer is that they can't. So in the realm of confidentiality, you have a lot of different ways that contracts can be interacting. And if they don't interpret operations and values the same, you basically need to bridge between them. We built a lot of extensions at OpenZeppelin. If you want to experience 7984, you can look at our repo and build with these extensions. And then without further ado, I'll jump into a quick little demo here. If anyone wants to follow along, you can follow along with the whole thing. We're going to use the OpenZeppelin wizard and then a little command line interface to help you interact with the token that we're going to deploy. So, oh, the internet's working. OK. So I recorded this in case the internet wasn't working. But we go to wizard.openzeppelin.com, click on confidential, and we have a section for the 7984. Name the token, specify a symbol. And by the way, this was actually released this week. So this is all brand new tech. And if you want to deploy a confidential contract, well, you'll see it right now. We'll do a pre-mint of 10,000 tokens to ourselves. And we'll leave the rest configured as is. We'll be using Zama. We'll open it in Remix and follow these instructions. We're going to add the remapping as the wizard described, so remapping.txt, and paste the remappings that wizard gave us. Save that and go back to contracts to compile. Now we'll head over to deploy the contract, the Ethereum with an arrow, and we'll select our injected provider, MetaMask, and deploy to Sepolia. We have to specify a receiver in the constructor, so that will send to the deployer address. And we'll wait for a second for this to be deployed. Once we get the contract address, we'll pull up the command line interface, which is a separate repo that was on the second QR code over there. Again, right, these are all handles that are encrypted, so you need some tooling to actually see what's going on with them. So you can see the command line interface pasted in the token address, and it's fetching the deployer balance, decrypting the balance. The handle over there is the balance that's stored on-chain. And you can see, so we have 10,000 ETHDenver in this wallet. And now we'll go to do a transfer. So the transfer parameters is the token, the amount, and the to address. And we'll encrypt this amount off-chain, right? So we generate a new handle and a proof, an input proof, which verifies that we know the value of this handle, so we can utilize it on-chain. And in a second, I'll show the actual input proof on Sepolia scan. So we have the transaction on Sepolia, sent 20 ETHDenver to the other address. And while this resolves, we'll check my balance again to see that it was deducted. So we should have 9,980. And as Sepolia scan indexes, we'll see what the inputs for that transfer were. So again, right, we did a transfer for 20 tokens. And there. So the 20 tokens, we have the encrypted amount, which again is a handle, and then we have a ZK proof that we know what that value is. Okay, and we have a few minutes for any questions. If anyone has any questions, thank you for listening. This is a QR code for the confidential contracts library that we've been building at OpenZeppelin, and any contact information if you have questions afterwards. Any questions? Nope. Okay, thank you.